Howdy, y'all. Happy Wednesday. I really hope it's Wednesday. It'd be embarrassing if it wasn't. I think it is. I'm getting my days mixed up. They really fly by. We've been doing a whole lot of fun stuff here at Topple. Sorry, it's been a couple weeks since I've given an engineering broadcast like this. But I still have been hard at work. This time, I'm gonna be talking about consensus state with y'all today. It's gonna be a party, if we agree. I don't know if y'all will agree with me, but that's kind of the point of consensus, isn't it? Okay, let's hop in here. Got some diagrams and a couple of words here. I don't know. I don't really do the whole words thing very well. That's why I'm a programmer. Yeah, indeed. Hump day. Hump day. Alrighty. Consensus state. So, Topple, our blockchain. We're dealing with proof of stake. I'm not talking about beef here, although I had a pretty mean steak the other day. It was good. But in this case, the stake that we're talking about here it's like almost like an investment, a monetary investment into a network. All right, so something like Bitcoin, that's proof of work. Your investment into the network is energy. It's burning coal. All those dinosaurs that gave up their lives, millions of years ago, and we're turning them into little magical coins. Thank you, dinosaurs. You did great, but we're running out of dinosaurs, so we need something that doesn't really use as much energy. So that's where proof of stake comes into play. Okay, so as I mentioned, you're investing into the network, but it's more of a financial investment. Okay, so instead of investing energy, you give up a little bit of money and you say, okay, so I believe in this particular network, this particular blockchain. I'm going to invest in it. And in return, I get staking rights. Staking rights basically means that you can either mint blocks, like create new blocks to extend the blockchain, or you can have someone else make blocks on your behalf. We'll get to that later. That's called delegation. We haven't quite gotten there yet, but the smart folks over at IOHK have this really cool plan for it. So it's not a totally novel idea. I'm not that clever, don't worry. We'll get to that eventually, though. Okay. So here in proof of stake, however, when you go to mint a block, let me back up. When you want to try to mint a block, you first need to be eligible for minting a block. Okay, so eligibility is based on a little bit of randomness, and then it also factors in how much stake you have in the network. Okay, so your relative stake, compared to the rest of the people who are also trying to make blocks, determines how frequently you are eligible to actually produce a block. And if you produce a block, then you get some rewards. You get a little bit back in return for spending the time and like running a blockchain node. So that's the whole point of proof of stake there. The more stake you have, the more chances you get to mint a block, the more rewards you get. So invest, or whatever the meme is. Okay, so how do we actually do that, though? Well, when you go to produce a block, it's you get like an eligibility, and then that gets kind of stamped on the block, and it needs to go through like an eligibility certificate process. But then other nodes need to go and validate that eligibility certificate. Were you eligible to actually make this block? So to do that, you need to essentially verify what amounts to the random number that they came up with, and make sure that that matches like the stake that went into coming up with that random number. That needs to match what other nodes think is on the chain. How big of the piece of the pie do other nodes think that you have as far as stake goes? So other nodes need to be able to determine that. Now, usually, this would ordinarily be pretty straightforward, determining how much stake someone has at the tip of the chain, but it's actually kind of complicated when we're talking about. I can't remember exactly when in Ouroboros it came about, but it's this concept of lagging. Okay, so you don't make your decisions based on what's going on around the tip of the chain. You need to make your decisions on what happened a few days ago. And that's so that people can't really bias things up at the tip of the chain. There's this thing called like a stake bleeding attack, and it has to do with rewards and whatnot, and that kind of alters the stake distributions in a weird way that becomes kind of unpredictable. My teammates they'll be way better at explaining all of that. They're the smart people. I'm just the typer. So stay tuned for future broadcasts. Hopefully in one of the upcoming ones, you'll get to hear from one of our super duper smart people about how all of this magic works. Okay, so as I mentioned, in order to validate a block at the tip of the chain, you need to base that decision on historical data. In this case, data from what we call 2 epochs ago. Okay, so it's data that happened or that took place previously. So it's a historical decision. And that decision includes how much relative stake did someone have, and were they actually registered? Okay, so I guess that's another thing that I didn't mention. Here in proof of stake, you have to go and register on our blockchain, indicating that you intend to create blocks in the future. Or as I mentioned, you could intend to delegate your stake to someone else, but that'll happen later. But you do need to register and indicate your intent to produce blocks, and you also need to establish your initial registration randomness, essentially. So you're committing to a random value ahead of time, and then you can use that random value to determine your eligibilities later. You need to register that so that other nodes can go and validate it, though. So that's kind of why registration comes into play there. There are other nuances to it, of course, but that's kind of like the simple reason. Okay, so registration and relative stake. Those are the two main things that you need to know in order to validate a block. I guess the two stateful things that you need to know in order to validate a block header. Okay, so that was a whole bunch of rambling. Let me try to hop in and explain a bit of the mechanics here. Okay, so we've got a blockchain. You can imagine these red circles here. These are block headers. And so this red circle right here, this points to its parent block, and that points to its parent block, and that points to its parent block, etc., etc., all the way up the chain until, well, I mean, this isn't actually the tip of the, or sorry, this isn't actually the genesis block. There would be more here, but it just continues. Headers connect to parent headers. Okay. So these headers all took place within what we call Epoch 7. Okay, so an epoch is a time scale within the blockchain. And that time scale is based on a unit of time, a discrete unit of time called a slot. And so your genesis block, it starts at 0, and then it moves forward slot by slot for infinity. And a bunch of slots, let's say 10,000 slots, make up one epoch. And then you could have, well, in this case, we have 37 epochs. So we're 37 epochs into our blockchain here. Again, it's a unit of time. You can map it back to like a literal clock value, and to some extent at least, but it's particular to proof of stake blockchains. Okay, so we've got our chain of block headers here, and we've got this header right here that we are attempting to validate. So let me actually just change its yeah, there we go. So we're validating this block X. But as I mentioned, in order to validate block X, we need to make our decisions based on data that happened 2 epochs ago. Okay, so if you want to think of it like one epoch is a day, and so within that day you have so many slots to account for an epoch. Oops, sorry, open the wrong tab elsewhere. Okay, so in order to validate block X here that belongs to epoch 37, we need to go and look at data that took place at the end of epoch 35. Okay, so that was 2 epochs ago, 2 days ago. That's what we're making our decisions on. So in order to validate a block that was produced in day 37, we need to go and look at data at the end, right before midnight of day 35. Or sorry, we're on day 35. It's at the end of the day, whatever, 11:59 on day 35. There we go. 11:59 p.m. or 23:59 for people who use school time. So yeah, epoch 35, it needs to be the very last block of this epoch. So all of the transactions that took place up to and including block B here get considered in our stake distribution, so the relative stake of each block minter, as well as who is registered to actually mint or produce a block. Okay. So in order to so step one, we need to figure out our reference point, our epoch boundary. So the reference, the block that we need to reference to validate block X is block B. Okay, so in order to make that determination, we need to use our event-sourced state concept. I've talked about this a few times previously. We use it in different parts of the Tetra code base, places like the mempool, semantic validation to track box state. We have a block height tree to determine the block associated with a particular height along the canonical chain. There might be a couple others that I'm forgetting at the moment, but this is going to be yet another use case for it. Okay, so we have an event source state, which, just a brief overview. It's like classical event sourcing, where you apply events to a state to produce a new state, and you just keep doing that over and over again for any new events that come into play. In this case, instead of an event, we're talking about blocks. So we're applying a block to our current state to produce a new state. But in the case of a blockchain, blockchains are actually more like this tree structure, in that this block here, because of the concept of network delay, it may have 2 different children. And depending on the chain selection algorithm from consensus, it'll select one or the other. So we end up with a tree structure. And because it's a tree structure, we need to use slightly different mechanics than classical event sourcing. So we have an event tree that leads to this event-sourced state. And we're using that event-sourced state to capture an epoch boundary state. And this state is essentially just a mapping from an epoch number to the last block ID of that epoch. Okay, so in this case, the last block ID of epoch 35 would be block B. And then, epoch 34 would be block A. Epoch 36 would be, I don't know, F, something like that. Doesn't matter. So it stores the block ID associated with the last block of each epoch along some particular canonical chain. Okay, so that's one event source state. So to use it, we're hooking into consensus validation state, and we're validating block X. So we know that block X belongs to epoch 37. So 37 minus 2 is 35. Okay, so this method call is saying use the state at, then we specify like the head of the chain for which we are basing this decision. You know, the sequence of blocks that we want to consider. And then using that, we pass in epoch number 35 into, you know, this storage function. So the key 35, and we want to get the value, so some block ID. So out comes the letter B, or sorry, the block ID B, because that's the end of epoch 35. So now we at least have our reference point. We know at what point in the chain of data do we need to go and fetch the information that we care about for validation purposes. So like I mentioned, we care about the block minter's relative stake, and we care about the block minter's registration. Okay, so got a quick question here. What happens if there is a reorg across an epoch boundary? So a reorg is essentially, let's look at, you know, this right here. Let's say that we were, well, maybe this is a bad example. Let's look at, you know, this one right here. Okay, so this block, whatever block this was, it has two children, this block and this block. And then, you know, let's say this chain got continued a little bit further, and, you know, it took us out to here. Then all of a sudden, we heard about this other chain, this one down here, and using our, you know, chain selection mechanism, we decide that this particular chain is better than the one that we had before, this one up here. So we need to do what's called a reorg. So that means that we need to undo some things. So we need to undo any changes that happened in this block. Then we need to undo any changes that happened in this block. And then, oh hey, we're in a common ancestor state. So now we need to apply blocks forward. So we need to apply this block here, and then we apply this block here. And then now we have completed our reorg. But let's say we were unlucky. There we go. We were unlucky and we ended up here. And all of a sudden, then we hear about this chain down here. Well, it's somewhat of a bummer, because now our consensus state, it looks a little bit different, because the end of epoch 36 is a different block than, you know, this other chains. So that's reorging across an epoch boundary. Now, luckily in this case, it's only reorging across a single, like a single epoch. So when we go to validate, you know, any block here, like any block at this tip, you know, if this got extended, it's still going to need to reference the n-2 epoch block, which means it doesn't really matter if it follows this chain backwards or if it follows this chain backwards. As long as we still end up here, then it's not really much of a cost, because we're still going to need to compute the same consensus validation data, because it's lagging by 2 epochs in that case. Now, let's say we got like really heckin' unlucky, and I don't know, let's say something something like this. So now we got a rough situation. It's not the end of the world, but it is quite unfortunate, this particular one, where not only does it need to it still needs to reorg across across one epoch boundary, but it then needs to reorg across another epoch boundary. So now when you're going to validate, like a block out here, so you wanted to validate, this new block. Well, when you go and look up the reference block to base your to base your validation decisions on, you end up here instead of here. So now you need to base your decisions on slightly different data. In particular, I mean, the only real difference is the transactions that took place in block B versus the transactions that took place in this particular block. So it's not horrible because of what I'll get to in a second. It only needs to unwind back to this particular block and then play forward to this one. So this isn't like a super end of the world case. But anyway, yeah, so it needs to go and reference a different block here when it makes validations decisions about this particular block. So that's the first question. That was, addressing this question right here. What happens if there is a reorg across an epoch boundary? Well, it just needs to make a different decision about which reference point. But then there's the follow-up question. Is the boundary state updated? And so this is kind of a fun one, because down here, if we are following the event source tree of this particular chain, then the values stored in our epoch boundary state down here, this thing here, for epoch 35 as the key, the value is now, really should just give this a letter, B2. Sure, let's go with that. Yeah, giant oval, that's what I wanted. That's fine. Anyway, so now epoch 35 now points to block B2. And so this value that gets returned here, if we were validating X2, we'd be using X2 here, and then our result would be B2. So we would just get a different reference block ID to use. So to answer the question, yes, the boundary state would get updated with a different value associated with epoch 35 and also epoch 36. Okay. So let me go ahead and undo a couple of these things. Get rid of our giant oval because that looks ridiculous. Better. Okay. So we know how to get to our reference point. So we need to validate, in order to validate block X, we need to use the data from block B. So we've got our reference block now. We know what to point to. Now the data that we actually need is relative stake and the registrations. So we need another kind of state down here called, I changed this, consensus data. Change this to operator stakes. So as I mentioned, okay, so yeah, we have this consensus data, and this is where we have the things that we care about, like the actual data values that we care about for validation purposes. Okay, so operator stakes. So An operator is just another name for a block producer or a block minter. It's just different terminology. They all generally mean similar things though. But it's the person producing blocks, or I guess the computer. I don't know. Computers are people too. I guess it depends. So we need to store the staking values. So the number of dollars owned by each staker. We call that the usable stake. In the case of Topple, our blockchain calls that the arbit. So it's a type of token used for like our stake value essentially. And that's for each active operator. Okay, so that's the storage, and it's a mapping from like an operator's staking address to a 128-bit integer. So a really, really heckin' large number. And that's just the number of arbits that they have. Okay, so that's operator stakes. Then we have another storage, and this just stores a single value. So total stake. And it's just basically the sum of all of the values in the operator stakes. But we want like we just want a separate value to make it easy to look up. Okay, so it's all of the arbits currently in use for staking. And we can combine these two values in order to determine someone's relative stake. Okay, so if Jeffrey, the node operator, has 37 arbits, and there are 100 total arbits, then Jeffrey has 37% of the stake, or whatever number I said. I already forgot. So that's how you can determine the person's relative stake, and that gets captured as a ratio value. Okay, so those two things combine together. Then this other thing down here is registrations. So this stores the registration box for each operator. So again, it's a mapping from operator staking address to, well, this b.v.r stands for box.values.registrations.operator. Okay, so it's an operator registration. Okay, so those three things all combine into this consensus data. And our goal is to determine the consensus data at block B. Okay, so that's how we're combining these two event source states together. So this event source state helps us determine using block X that we need to reference block B. And then block B helps us determine our relative stake and our registrations. And so we just combine those two pieces together to be able to validate block headers in a lagging fashion, or using data that lags behind the tip of the chain. Okie dokie. So we are about 30 minutes in. Going to turn on the music so that I can grab a quick drink, see if there are any questions. So type away. I love it when I do a perfect job explaining and there are no questions afterwards. I must be a genius. Okay, let's move on to what I've got for code so far. So consensus validation state algebra. So we've got two methods in here. operator relative stake and operator registration. You can see they both follow the same general format here. So we want to determine an operator's relative stake at a particular block ID. So current block ID, for example, block X. So this is the one that we're validating. And we want to get the relative stake associated with this particular operator address. And out comes an optional ratio. And so ratio numerator, denominator. Okay, so this is Jeffrey's stake, 37 arbits, over the total stake, 100 arbits. Okay, so that relative stake goes and feeds into like the VRF and eligibility stuff, and we're happy from there. We can continue that validation. The second thing here, operator registration. I'm sure y'all can figure it out. It does the same thing. We want to get Jeffrey's registration at block, well, using, like, we're validating block X, and out comes Jeffrey's registration at block B. Okay. And again, so that registration gets used to verify their commitment at the beginning of their registration, essentially. Okay, so these two methods will get used by block header validation, which, it's not currently hooked up, but we can see how it's using some of the older things here. So we got a question here. What happens if Jeffrey is the only active operator? Does the chain go slower? So that'll depend. Like, is Jeffrey the only registered operator? In which case, Jeffrey would presumably control all of the active stake, which means that the blockchain shouldn't really go any slower as far as I know. But if there are 100 people registered to mint blocks, and Jeffrey is the only one currently running a node and actively minting, then our blockchain is going to go super slow, because Jeffrey only has 37% of the stake, and that other 63% is just like, well, so yeah, it's not being considered, and therefore, like, the blockchain is not going to grow as quickly. And so could you clarify what you mean by active stake? Okay, so the denominator in the ratio is modified. Oh, okay. Okay, so yeah, let me answer this one real quick. So the denominator in the ratio is modified each epoch. I believe so. It may not modify by very much, but people may come and go as registrants, and if they aren't, well, it's still like to be decided, I guess, technically, if we allow people to register without any active stake, or if we allow people to, like, send stake to someone who's not registered. Those are still kind of open questions. But in general, yes, the total active stake combined between all active minters, it can change epoch to epoch. Now, we don't have this thing called inflation quite yet, which means that, like, the number of arbits total overall within the entire system, even inactive, would grow. So that would be inflation. We don't have that imposed quite yet. That would be another way in which the denominator in this case would grow. Now, what do I mean by active stake? Okay, so let's say we have like 1,000 node pools. Well, I'm not going to say pool. Let's say there are 1,000 nodes all operating, but we have millions of blockchain users, and one of those users could be like a crypto exchange where people are buying and selling our tokens using US dollars, for example. So that crypto exchange, I mean, they may hold on to like a whole bunch of arbits, like maybe even like half the pie. It's like half of the arbits on Topple's blockchain may be held by like an exchange somewhere. And if it's held by an exchange, it's really not fair if that exchange gets to use those arbits for staking purposes. Okay, so we have what's called an exile, or non-staking, I guess, is what it's meant to be. So those are arbits that are controlled by things like an exchange, these big whales that it wouldn't be fair for them to use it for staking. But we don't want to consider those arbits when we are making proof of stake calculations. So the total active stake does not include the arbits held by crypto exchanges, for example. So it's only the stake held by people either minting blocks or people who delegate to people who mint blocks. So it's only those two things is what's considered in active stake. Alrighty. Yep, not a problem. Happy to answer. Those are great questions. Thank you. Okay, so these are the two things that we care about here: operator relative stake and then operator registration. At the moment, our block header validation is hooked up to different means of retrieving that data. So right now we have a relative stake interpreter and we have a registration interpreter, and I mean they're based off of different things, and they don't consider like a block tree, for example. And at the moment, it just returns static data. So the whole point of this body of work is to do dynamic consensus data, essentially. So how do we use these right now? Well, let's look at like relative stake interpreter. Find the usages of this. Okay, so we are using the relative stake interpreter, so the thing to determine the minter's relative stake. We're using that to determine their VRF threshold as a ratio. And so this VRF threshold is, again, what gets used in eligibility determinations. So we look up their relative stake, and then we plug that relative stake value into this get threshold thing. And then the rest of the validation logic continues from there. And then let's look at how we're using our registration interpreter here. So registration verification, we verify the staker's registration. First checks that the staker is registered at all. And then once retrieved, the registration contains a commitment or proof that must be verified using the 0th time step of the header's operational certificate's parent verification key. My goodness, that is way too many words. Whew. Okay. The proof's message is the hash. I don't need to read all of this. That part's not important. All we care is like this registration, it stores a hash value that we need to go and verify here in block header validation. Okay, so we need to go and get their registration from the chain. So that's where we call our registration interpreter and do .registration of blah, blah, blah. Okay, so right now it's using two different interpreters, but they're instead going to connect to this algebra, different algebra, and the arguments are slightly different here, but they're more accurate in this case. So yeah, I haven't integrated this quite yet, but I at least have the start of an implementation. So let's look at that. So this, again, this is just an algebra. So let's go look at the interpreter. Okay, so consensus validation state. And here I've got, this is case class consensus data. Oh, stop scrolling. What? Oh my goodness. This poor laptop. Okay, consensus data, this big magenta box. I don't know. People who know colors better than me can comment. Is this magenta? Is it pink? Is it purple? Is it red? I could really confuse everyone. Call it green. I'll call it magenta. So consensus data stores operator stakes, stores total stake, and stores registrations. Peachy to me. I could see peach. I think peach works. Especially because it's on like this orangish background. Like if you mix those two colors, it's a nice solid peach. Yeah, I could get behind that. Okay, so this consensus data maps basically to this case class, as you can see here. So operator stakes is just this mapping from staking address to number of arbits. And then total stake is just a storage that has a single value in it of the total. I guess this really should be total active stake. Oh no. Okay. Total active stake. And then finally, registrations. So that's our consensus data. And then we have this epoch boundary state. So it's a storage from epoch to block ID. And that's what we have here. So epoch boundaries, storage from epoch to block ID. It's the last block ID of each epoch. Okay. And then in order to make, this consensus validation state algebra instance, so the instance of this thing here that we were just looking at, we need these things. We need a function to go and look up a header. Why do we need that? Oh, okay, yeah. We need a function to look up the current header that we're validating so that we can go and extract the address. Plus, I think there's another reason that we needed it. Anyway, we need to be able to look up the header. Second thing is the epoch boundary event source state. So this yellow box is what we need. Third thing is let me rename this consensus data event sourced state. Okay, so we need this yellow box. And finally, we need a clock. And we need this clock in order to tell us which epoch this particular header is in. Okay. So how do we interpret this? Well, when we want to determine an operator's relative stake at block X, for example, we need to go and fetch block X, or block header X, I should say. And then we need to call into this use state at target boundary. And this is basically just a helper method that calls into this event source state to determine the block ID that I need in order to call into this event source state. Okay, so use state at target boundary. So first, we need the current header. From the current header, we can determine its epoch. So 37. And then we need to subtract 2. So 35. And then Once we have our epoch number 35, we plug that into this epoch boundary event source state to determine the block ID at the end of 35. So that's our boundary block ID, which is B, this one. And then using block ID B, we call our consensus data event source state and we pass in block ID B, and then we just invoke whatever function was passed in here. So some sort of function f that uses this pink consensus data, sorry, magenta. It uses this thing to produce some sort of result. So in the case of our block header validation, we would use consensus data to produce the minter's registration as well as their relative stake. Where was I? Right here. There we go. Okay. So yeah. Now that I'm looking at this, I might collapse this into a single method that returns a tuple containing both their registration and their relative stake, just because you pretty much always need both, and they're both accessible at the same time anyway. So I think that would make sense. I'll leave it to do. No, stop. Okay. So maybe collapse into a single method returning relative stake and registration. Question mark? And we'll figure that out later. In the meantime, we'll just move forward with them being separate. Okay. So for now, we're determining just their separate relative stake. So Jeffrey's relative stake at block X. We need to use the state at block B to get this consensus data that we care about. And using that consensus data, we go and look up in the operator stakes for their address. Out comes an optional int 128. And using that int 128, we can call into consensus data.total active stake to determine our denominator of the ratio, which, again, that's what our ratio ends up being here. Let me rename this here, total active stake. Cool. And so this is the relative stake. It's just, this ratio here. Okay, so that was the relative stake determination. Then operator registration is pretty much the same exact thing, except instead of calling into the operator stakes and total active stake, like sub data stores, whatever, we're just calling into the registrations to go and fetch their associated registration value. Okay. So once we have these two event source states already made, it's pretty straightforward how to implement this interpreter. Constructing these two things is a little bit less trivial. So that takes place down below. So our epoch boundaries event sourced state, because I'll just read the description. So it's an event source state which operates on an epoch boundaries. And so in order to do an event source state, or like implement one, you need basically these two functions here. You need the ability to apply an event, and you need the ability to unapply an event. So applying a block to our epoch boundary state depends on whether or not that particular block crosses an epoch boundary. If it crosses an epoch boundary, then its parent block is added to the epoch boundary store. Otherwise, it doesn't do anything. Okay, so looking back up here, let's say it doesn't really matter. Let's say we were at this block right here, this red circle, and then we moved to this block. Okay, so we crossed an epoch boundary, which means that we need to declare that the end of epoch 36 has this particular block ID. And so we save that into the store. And so that would happen anytime we cross an epoch boundary. But if we don't cross an epoch boundary, so like, this case right here, we were at this block and then we moved to this block, well, nothing needs to change in the store, so it's a no operation. So that's applying a block. Unapplying basically does the reverse. Okay, so if we were at this block right here, then we needed to unapply, and then we need to unapply it, then we realize that we're crossing an epoch boundary, and we therefore need to remove this particular block ID from our storage, because it may no longer be the final block of the epoch. There may happen to be another one that sneaks in, within that epoch. So then this would be the epoch boundary. We could theoretically detect that this particular block landed on the exact slot that puts it on the boundary, and therefore there could not possibly be any other extension of it that lands in the same epoch. But I'm lazy, so I didn't do that yet. Get to it eventually. Okay. So yeah, so that was unapplying a block. So to implement that, so apply block takes in a state, so an epoch boundaries, as well as a block ID to apply. So if we want to apply this block, then we need to go and fetch its slot data. And that slot data contains, well, the two things that we care about from it are its slot as well as its parent slot. Okay, so we use those two values to determine the epoch. So the epoch of the block that we're currently checking, as well as the epoch of its parent. If those two things are the same, then that means that we didn't cross an epoch boundary, and so we could just continue on and don't do an operation. But if it did change, then we need to add the parent block ID to be the value associated with its epoch. So that's applying. Then unapplying is the opposite. We simply remove the value. Then we produce our event source state. Okay, so this one was relatively simple. The epoch boundaries event source state, because it's really just storing, this. Oh, geez, not that. Storing this value and this value. Well, I didn't want you to select all of them. Storing A and storing B and storing whatever the heck that one is. So it's only got to do a few things. This other one down here, consensus data event source state, is way more complicated. And it's also incomplete. This is just like the very basic of it. And it doesn't consider delegation. It doesn't consider things like rewards. So there's still going to be quite a bit more that needs to be bolted onto this. But, for now, applying a block will update the total and the individual arbit stake values according to the transaction. Okay, so any arbits that were spent in the transaction get subtracted from any staking parties, and any output arbits, so like new arbit boxes, are added to the corresponding staking parties. And then similarly, whenever you spend a registration box, you become deregistered. And then whenever you create a new registration box, you become registered. Unapplying a block does the reverse essentially, and it quite literally does it in reverse. So we consider the outputs first. So any output registrations, well, sorry, not only do we consider the outputs first, we also need to consider the transactions in reverse. So if the block has transactions A, B, and C, well, in order to unapply them, we need to unapply C, and then B, and then A. In particular, we need to unapply the outputs of C yeah, I guess I didn't finish typing this. That's fun. Anyway, we need to consider the outputs of so any output registration boxes, we need to deregister them, which sounds weird. Again, we're in the unapply block territory, so if they registered, then we need to deregister them. And then any input boxes, so any operator registrations that were spent by the transaction need to be re-registered, so they become, valid registrants again. And then same thing for arbits. So any output arbits, they need to be subtracted from the stake of the staking party. And then any spent arbits need to be re-added to the staking party. Okay. And then the implementation, I split it out a little bit so that the apply function is now literally a class called apply block that extends, well, the function signature that we need for an apply block. And then same thing for unapply block that extends, the same function signature, but for unapplying. But the implementation is quite a bit more complicated. Now we are right at time though, at least for me, because I'm tired. Talking's hard. So I'm probably going to pause it here. See if anyone has any questions about what I covered before. So maybe not the implementation details of consensus date, event source state, but I could talk about the high level of it, or epoch boundaries, event source state, or anything here in this diagram. Happy to field any questions you may have. While I drink some more water. Got us a question here. How does registration work with Genesis? Is there a pre-mine? So that's a great question. As I said, one of the steps in validating a block header is you first need to go and get their registration. But how the heck is anyone registered if the block starts, or is the blockchain starts from zero? How would a new block even be produced if no one's registered? Once the blockchain's already gotten going and we have people registered and whatnot, and we have people producing blocks and everything, all is fine, because those block producers can go and add in new registrants and help other people register and get them going on the blockchain as well. But in order to get the ball rolling, we do need an initial set of registrations. And this gets even more complicated because of this n-2 thing. So imagine we're all the way back at Epoch 1. Well, how do we go and get registrations from Epoch -1? Isn't that one heck of a fun problem to have? So in order to do that, we do need an initial set of registrations that get encoded into either the Genesis block or into the protocol. That's still to be determined. We don't know exactly quite yet. But it will need to be encoded somehow, just so that people can go and produce the block at height 2. It's a weird problem to have. It's getting block number 2 minted. Oh joy. So yeah, that'll definitely be upcoming. And well, yeah, I'll definitely need to do that before I finish this ticket. Otherwise, our Tetra Super demo is going to be very Tetra non-super, because it's going to do exactly 0 things. We're going to see 0 blocks be produced because no one's registered. It'll be a very sad day. So yeah, I got to get that one figured out. Got to get a Genesis set of a Genesis set of registrations as well as a Genesis Arbit distribution. So yeah, good question. Thank you. Do we have any other questions? Awesome. Alrighty. Well, I appreciate y'all being here. It's a fun Wednesday. Really like talking through all this stuff with you guys, mostly because I like to talk to myself, but it makes me seem a little bit less crazy if I'm talking to other people while I talk to myself. So thank you for that. I appreciate y'all being here, being my rubber ducks. You're the best. And yeah, I hope y'all will tune in tomorrow. Be doing another scheduled broadcast. So yeah, stay tuned. That'll be 4 p.m. Central on Thursday, July 14th. So yeah, thank you very much. I will catch y'all later.